Hello and welcome to Honors Function. In this first video of the first unit, we're going to review some terminology and notation about sets. So what is a set? A set is a collection of objects. We could represent the set with a bag or a potato like that. Suppose the name of the set is A. We often use capital letters for names of set. A set has objects either in the set, inside the set, or outside the set, okay? Let me give some name to these objects. Suppose this is A, B, C, and suppose this is X and Y. How do I specify that A or B or C is in set A, right here, and that X and Y are not? Simply, I write A, and I use this letter, it's like a capital epsilon in Greek. A is an element of, you read this as is an element of set A. Okay, this is an element and this is a set. Likewise, B is an element of set A and C is an element of set A. Okay, these three objects are all in set A. Well, how do we say that these two are not element of set A? That's easy. We say X is not an element of, you just cross it out, set A, and Y is not an element of set A. Okay? Like that. All right. There are various sets in mathematics. Sets of numbers, sets of matrices, sets of functions, sets of sets also. Okay? To write a set of numbers, we often use braces. So let me remind you of the three grouping symbols often used in mathematics. You have parentheses, okay? Parentheses. You have brackets, okay, these are brackets, brackets, and you have braces, these are braces, okay, these are the three grouping symbols we often use in mathematics. To write a set, we often use braces. There are two types of sets in mathematics. Sets that contains a finite number of elements, for example 2, 3, and 7. This is a finite set and it contains 3 elements. And sets that contains an infinite number of elements, for example 0, 2, 4, 6, 8, and then I'm going to use this right here, it means etc. If I use this 3 points, you have to understand the pattern. Of course, these are even numbers, okay? If the pattern is not clear, I cannot use this right here, all right? So you need to understand the pattern to write that. This is an infinite set of elements, okay? So there is another way to write infinite set of elements. For example, I can say the set of elements X, so I'm gonna call that X, such that, and here I can write the condition. This is read as such as, okay? It's very specific, such as, such that. And after that symbol, you just write the condition. For example, 2x plus 5 equals 0. So what is that set made of? Well, that's very simple. This is just the set containing one element. It's called a singleton, and it's -5/2, right? So of course, we wouldn't write a set like that for something that simple, but I'm just showing you how to write a set, okay? All right, let's move on. Let's recall now the 5 sets of numbers you've studied before. So please make sure you remember the name and the notation. The first set of numbers is a set of natural numbers, so it's a capital N with a double bar at the beginning. Set of natural numbers, and this is just the counting number, 1, 2, 3, etc., etc. Okay, this is a set of natural numbers. Natural numbers. Okay. The second set is a set of integral numbers. So the set is denoted with a capital Z and a double bar in the middle right here. So what is it? It's all the natural number plus the 0 plus the negative. So I'm starting with dot dot dot. Then it's -2, -1, 0, 1, 2, 3, etc., etc., etc. Okay? So this is a set of integral numbers. Integral numbers. Commonly, you will hear people call it, or in books too, a set of integers. Okay? Integers. This is a set of naturals. you make the adjective a noun, okay, and you put an S at the end. The third set is a set of rational numbers. We call it Q, and there is a double bar in front right here. So what is this set made of? So I'm going to use the notation I've just described above. So this is a set of elements written A over B. Now I need to give you the property of A and B. So A is an integer, okay? So A is an element of Z, and B is also an integer, but it cannot be 0. So I'm using a notation we haven't yet seen, Z minus 0. I could have written that B in Z and B different than 0, but it's shorter to write it like that, okay? This is the same as B in Z and B not 0, okay? So you cannot divide by 0, basically, okay? So this is a very condensed way of writing the set of rational numbers. Okay, then two more sets. You have the set of real numbers. Real numbers, it's R with a double bar in the middle, okay? So this is a set of real numbers. I cannot describe to you what it is. We don't have yet enough tools. We won't have the tools this year to go over the construction of R. There's a fundamental difference between R and all the other sets. I'll talk about it in some other lecture. And finally, the last set you've studied before is a set of complex number. So what is that? This is a set of elements written A plus IB. All right, so I need to describe to you what all these letters are. A and B are just reals. Okay, so I'm going to write it like that. A and B are real number. And I is such that I squared is equal to -1. All right, so this is an important set. We'll play with it a little bit in few units, okay? All right, let's go over some example now where we'll apply the notation we've seen. All right, so in the first set of examples, you have to use a notation is an element of or is not an element of, and you have to write the relation with all the set we've covered. So 4. So 4 is an element of the natural number. 4 is an element of the integer. It's also an element of the rational number. How come? Well, 4, for example, is equal to 4 over 1, right? If it's a rational, you have to write it as A over B, don't forget, right? So I can write it as 4 over 1. It's also a real number, okay? And it's also a complex number. Why? So a complex number, remember, it's A plus IB, right? So it is just 4, which is a real number, plus I times 0, okay? So it's also a complex number. So 4 is in all previous set. I'm going to let you deal with example 2. Let me do example 3. Got to be careful with this one. This is negative 3.25 divided by 0.25. Now, 0.25 is 1/4, right? How do you divide by 1/4? You multiply by 4. So this is the same as negative 3.25 times 4, okay? So if you time by 2, that's negative 6.5. If you time by 2, that's negative 13. So negative 13 is not, let me take this one. So negative 3.25 over 0.25, this is too long to write, okay, is not a natural number, but it is in all of the other sets, so Z, Q, R, and C, okay? And please do number 4. Let's move on to the next set of examples. So in this set of examples, you have to list the elements in the following sets, okay? So I made a mistake in my notes here. Please, X has to be an element, a natural number, including 0, okay? There will be too many elements. I'll show you the difference, okay? So X is a non-negative natural number, okay? So non-negative natural number. Why non-negative? What's the difference between non-negative and positive? Well, 0 is not positive, okay? 0 is not positive, and 0 not positive, not negative, okay? 0 is neither positive nor negative. So if I say positive, positive means all but 0. 0 is not positive, right? So 0 is not included here. If I say non-negative, 0 is not negative. So 0 is included in this set, okay? 0 is included in this set, and 0 is not included in the set of positive numbers, okay? So that's the difference. All right, so what's going on here? I want the non-negative natural number such that x is equal to 2n, so you're going to get very quickly familiar with this notation, and x is smaller than 16. What is 2n with n in z? So look at that. I'm going to take n in z right here, okay? So for example, I'll start with -3, -2, -1, 0, 1, 2, okay, etc., etc., etc. And let me get 2n. Let's see what that is made of. -6, -4, -2, 0, 2, 4, and all. So what are these numbers? They're just the set of even numbers. That's it, okay? They're just even. And there is also a notation for the set of odd numbers. You'll find it out on your own very soon, actually. Okay, so what is this set made of right here? What do I want? I'm going to erase a little bit here. It's getting very crowded. So what is the set made of here? It's a set of even numbers, positive even numbers, smaller than 16. Pretty simple, right? You got 2, 4, 6, 8, 10, 12, 14, and that's it. That's it. That's what the set is made of, okay? I'm going to let you do number 6 and number 7. Let's move on now to see relations between sets. Okay, first of all, a very important set, denoted like that, you know it. It's the empty set. Okay, it's also denoted, we write the empty set, I never write it like that, but you will see this sometimes. Just a set of braces without anything inside. This is the empty set. It's got nothing. Okay, it's very important. It plays the same role as 0 plays with number. This set plays the role for sets as 0 plays for numbers. Okay, so this is the empty set. All right, then sometimes the first relation between set is this one. Sometimes a set is going to be included in another set right here. Okay, for example, the set of positive even numbers 2, 4, 6, 8 is included in the set of integers, right? An even number is an integer. How do we write that? We say A is included in B, okay? So the included sign is smaller that the is an element of. The included sign is like that, is an element of, is a bigger sign. It's like that, okay? Do not confuse both signs. Please read my remarks on page 3 about the difference between these two signs. Very, very important, okay? All right, so that's when a set is a subset of another set. A is a subset. Another notation, what about if two sets have some elements in common right here, okay? Suppose that this is A and this is B. Then we have the element in common is A intersection with B. This is an intersection, okay? It's the elements intersection. It's the elements that belong to both A and B, okay? Then another relation, of course, you have the union of two sets, okay? A, B. What is A union B? It's all of the elements, so A union B. So this is a set of elements that belongs to A or to B. So you see, this is an AND, okay? You have to be in A and in B. And this is an OR. You have to be in A or in B. These are logical connector, and OR. And finally, one more set operation, very important. What about if you have A and B like that? A, B. What about, for example, this one right here? A only and not B. A and not B. So this is A minus B. Very simple. Okay, it's a subtraction of two sets. A minus B. And an important example of the subtraction right here is this set right here. All the real numbers except the rational numbers. What do we call this set? We call that the set of irrational numbers. So I'll talk about it in class more. There's a lecture on it later coming up. This is actually very, very important, and finding numbers in there is also quite important. Okay, let's finish with some more examples, and that will be all for this first lecture. Okay, in the first example, we have an intersection right here of two sets. What is in the first set? Well, we've seen this one before. 2n such that n is in Z, this is a set of even numbers, okay? All right, so I'm intersecting the set of even numbers with what? 2n plus 1. Well, hey, 2n is an even number, right? What happens if you add 1 to an even number? It becomes odd, right? So 2n plus 1 is a set of odd numbers. Now, intersection between the set of even and the set of odd, so you want a number that is even and odd at the same time? Well, that is just impossible. This is the empty set, okay? I'm going to let you do number 9. Let me do number 10. So what's going on in here? Again, we have even numbers. I'm going to write that as the evens. Okay, what is this one? 3n such that n is in Z. Well, these are the multiples of 3's, right? 3 times n, multiples of 3, right? So you want the multiples of 3 that are even. Well, it's pretty simple, right? So what are the multiples of 3? You get 3, 6, 9, 12, 15, 18, 21, 24, right? But they have to be even. So here we go. It's every other multiple of 3. 6, 12, 18, 24, 30, 36, 42. All right, what's going on here? Is there a notation for this? Can I write that in a simpler way? How can you write a multiple of 2 and a multiple of 3 in a very compact way? Here's what I want you to find right now. N is in Z. Can you write that in a much more compact notation? Check out the number. 6, 12, 18, 24, 30, 36, 42. Hey, these are the multiples of 12. No. 8. No. 6. Multiples of 6. That's it. Okay? All right. I'll do 11, and then you'll finish the rest of the problem. So what's going on in 11? All right. I'm not sure what the question mark is doing right here. There shouldn't be any question mark. I have two sets right here. I have this one, and I have this one. So there are actually two questions there, okay? I'm not sure why. I guess I could have written two separate questions. So anyway, the set of x's such that the absolute value of x squared minus 5 is equal to 4 and a natural number. So what is this? Well, we need to solve this equation, right? So x squared minus 5 equals 4. How do you solve an absolute value equation? This is a way to write two equations. So this is if and only if. This is logically equivalent to x squared minus 5 equals 4, or, okay, x squared minus 5 equals negative 4. This is how you remove an absolute value with an inequality, right? You should remember that. So we have x squared equals 9, which means x equals plus or minus 3, or x squared equals 1, which means x equals plus or minus 1. So what is the first one right here? Let me call that A. This question could have been better asked. And the second one, the second intersection, I'm going to call it B, okay? So what is in A? In A, what do you have? So we have these four elements intersecting N. So what's left is just 1 and 3, right? What about in B? Well, you have the four elements intersecting Z. They are all integers, right? So we have four elements, and I can just write plus or minus 1, plus or minus 3. That's it. Please complete all of the other examples. Thank you for watching.